Hey guys, welcome back to the channel. So in the last two videos, we discussed Leetcode problems, and those were 2-sum and 3-sum. If you haven't seen those videos, then I would highly suggest that you watch them, and I have pasted the link in the description, and you can also find the links on this video. So let's try to solve another problem in this video, and this one is called 4-sum. Well, if you saw the last two videos, then the idea here is pretty similar. We want to find four numbers A, B, C and D. Well, the numbers are at indexes A, B, C and D. So the numbers are nums A, nums B, nums C and nums D, and these numbers are present in the nums, and we have to find the numbers such that they sum up to a given target. Well, in the problem 2 sums, the target was 0. We needed to find two numbers which sum up to 0. In the problem 3 sum, we needed to find three numbers in the array such that they sum up to a given target. So this problem is just an extended version of those two problems. The target here is again given initially to us, and we need to find such pairs, these quadruplets, such that they sum up to the given target. If you see the example here, then in the first one the target is 0 and we have to find such quadruplets. So these are -2, -1, 1 and 2, then -2, 0, 0, 2, -1, 0, 0, 1. So all of these three pairs, they sum up to 0, which is our target. And the condition is that the indexes should be distinct. So even though the numbers may not be distinct, we have to make sure that the indexes that we are considering here need to be distinct. And finally, we need to print the numbers, and they can be printed in any given order. In the second example, we have 8 such numbers, 2, 2, 2 and 2, and the given target is 0. Well, there is a slight confusion in the problem, because you can see that the indexes are A, B, C and D, and although we can have multiple such pairs, but we are given only one such pair. So I guess the condition here is that the pairs should be unique. So the numbers should be unique. That is, nums A, nums B, nums C and nums D should be unique. So in this case, we have 2, 2, 2, 2. And this is the unique quadruplet which sums up to the target, which is 8. So this problem is very similar to the 3-sum problem. There we had to find a given triplet such that the triplet in itself is unique. That is, we don't need to repeat that triplet again even if we encounter it again, and the numbers in the should target. Now if we look at the constraints here, the length of the array is 200. So this is a very big hint that they expect us to solve the problem in n cube complexity, and n cube log n, since we would be using the map data structure, and we can also solve this problem in n square complexity, but that is left as an exercise for you guys. So I hope you can try solving that in n square complexity. But for now, for the sake of simplicity and to explain another technique that I'm going to use in this problem, I will be solving this in n cube log n complexity. So let's get started with the code. So first of all, I will just take length of the nums array, which is n, so I don't have to keep on using that with the keyword. So I'm just saving it to an integer n, which denotes the length of the array. Now I will just iterate over the whole array. So I will fix the index I, and then I will iterate over all the indexes j, and now I'm fixing the index j and iterating over all the indexes k. So if you remember, in the 3-sum problem, we were fixing two indexes and trying to check the result that if we have encountered the difference, that is target minus the first index plus the second index number, if we have encountered that number before, if we have seen it previously, then that would be part of our pair. In this case, we are going to do the same thing, but now we are keeping track of 3 indexes instead of 2. So what I will do is I will create a mapping of seen index, that I have seen an index before. Now I have fixed the 3 indexes I, j and k. Then our interesting number, the number that we are looking for, or I should say the number that we should have already looked for, or we should have already encountered, is called as interesting number, which is equal to target minus the sums of the number I, j and k. If we have found that index in the array, that is, if we have seen the interesting number before, then this is a pair that we care about. So let's get a temporary array and append all these numbers to the temporary array. So I'm just appending all the indexes to this temporary array, although we don't want to append the index, but we want to append the numbers themselves. That is, we want to return those numbers themselves. But for now, I'm just keeping track of indexes because indexes are meant to be unique. as discussed in the problem, but we will see that it is not exactly right. So I'm just trying to run this to see if it compiles. Well, we are facing some error here because I have missed the colon operator. So now this should work fine, and clearly we are seeing this wrong answer because you can see that the output are the pairs of indexes or the arrays of indexes, but we don't want this output. We want the actual numbers. So the change is very simple. If you could have guessed, instead of using ijk and idx, I would just use nums of ijk and nums of idx, because I'm actually trying to get that number and not the indexes. So I will just append this to my return array and I will mark this number as seen because I have already seen this number. Now, what we want to do is we want to maintain the fact that if we have seen an array of numbers, if we have seen a quadruplet, we don't encounter it again. That is, we don't count it again. Therefore, what we need to do is we need to maintain the unique pairing. In case of the threesome problem, if you have seen the video, we maintained triplet struct and we were hashing that struct. But here, let's try to do things a bit differently. Let's try to actually break down how hashing might work internally. So first of all, what I'm going to do is I'm going to write a sort function. So I will just sort all the numbers, and this is a very simple sort because we know that we have an array of only 4 numbers. So the complexity of this sort function would be 4 into 3, that is 12. So we don't need to write any fancy merge sort or quick sort. We are happy with this simple bubble sort or whatever it is. We're just iterating over all the indexes, comparing it with the current index. If it is if it is less than the current index, then we are swapping that number. So this way we have a sorted array. Now the problem is that in the second question, you can see that 2 2 2 2 is pair that is being repeated again and again, because first we have 0, 1, 2 and 3, that is we are saving the indexes 0, 1, 2 and 3, then we are saving the index 0, 1, 2 and 4, then we are saving 1, 2, 3 and 4 and so on. But we don't want that. We want our array to be unique. So since we have already sorted the array, we can hash it. Now I'm going to try to use a different hashing technique here. So instead of making quadruplet struct and then hashing the struct, I'm going to write my own hash function. So let's define a modulus. The modulus is 10 to the power 9 plus 7, which is a prime number. And what I will do is I will write a hasher function. So this hash function will take in the array of length 4, that is our sorted array, and hash it to a given unique number. Now I will define a multiply function, which I will define shortly. And what I'm going to do is I'm just multiplying the number to 11 power I. So 11 here is a prime number. So write a simple hash function. What you can do is you can multiply the number at index I to a prime number raised to the power I, and then you can mod it. Multiply function, if you would look at it, is a simple function which just does a simple multiplication and then mods it. And power is again a simple function which is simply repeated multiplication. So initially the return value would be 1, and then we are multiplying the number with the return x times, since we are raising to the power x. So for example, 2 to the power 3 is 2 cross 2 cross 2, that is 2 multiplied by itself 3 times. So a to the power x is a cross a multiplied by itself x times. So that is a simple power function. Although this is not the most efficient power function, this can be done in log x, but I'm doing it in O of x because I know that the length of the array is 4, so my complexity won't exceed 4, and multiplication is simply multiplying two numbers and modding it. So this becomes our simple function of power and multiplication, and you can see how I'm rewriting or reusing a function inside another function to construct a complex function using some atomic smaller functions. So this is our hash function. Now what I'm going to do is I'm going to sort this temp array, and then I'm going to hash it, and then I'm going to say that I have already seen this quadruplet. Well, if I have not seen this quadruplet, I will just append it and mark it as seen. Now this hash function is deterministic. It will always return the same result for the same quadruplet because we are applying it in the same way. That is, we are sorting the array and then we are multiplying it with 11 to the power index, and then we are modding it. Why am I using the mod value here? Because I don't want my values to exceed very big integer limit. So that's why I'm modding the value, although I don't think, no, actually I think we will be needing this because the numbers, as you can see, range from minus 10 to the power 9 to plus 10 to the power 9. So that's why I'm using this mod function to keep it within bounds. And I know that I won't be encountering 10 to the power 9 values. So that's why I'm using a safe prime modulo operator. Well, I could have used struct2 for hashing here, but I just wanted you to get an idea of how hashing is used internally. This might not be the exact way, but this is the correct way to hash something for your own use cases. You can choose a different mod value for much more greater range and you're all set. Well, there are some errors, and after fixing those errors, I'm still getting some compilation issues. Maybe I need to do this float 64, but that is not the case. I don't think mod works on floating numbers. Okay, I forgot the thing which is int. So after writing that and trying to solve this problem, I get the accepted verdict, and this is how we use hashing function of our own. So we don't need to use the struct always, use the hashing function, and this problem can be optimized much more. That is, we can use a simpler sorting mechanism, and also we can use a better power function, but everything is O(n) complexity where n is equal to 4 because the length of our arrays are 4, so we don't worry about it too much. So this is it, guys. This is how you solve the 4-sum problem, which is very similar to the 3-sum problem, and you can solve an n-sum problem in n-1 complexity. So length of the array powered n-1. So 3-sum can be solved in n² complexity, 4-sum can be solved in n³ complexity, 5-sum can be solved in a 4 complexity, and you just need to append that log n factor for mapping, and this is it. And I'm just trying to explain everything very quickly as summary in the comments. So you can see that we solved this problem n³ log n complexity, numbers I, j, k, and something seen which we have already seen, and iterated over sums up to a given target. So I should be equal to target minus that seen number or the seen index. Therefore, seen index is simply target minus I, j, and k. And that is what we did. We fixed 3 indexes I, j, and k. We subtracted it from the target. That comes out to be an interesting number that we care about. And if we have already seen that number, it means that we have found our quadruplet. And if we have already seen this quadruplet, then no need to add to the array. If not, we simply have to add it to the array so that next time when we encounter it, we have that same deterministic hash value. And we know that since we have seen this quadruplet before, we don't need it. We don't need to add it to our array. And this is how we solve this problem. So thanks for tuning in. I hope you liked the video, and see you in the next one.